This is a video that will go over how to do a disaster risk assessment for earthquakes. In this video, we will walk through a demonstration of a scenario earthquake hazard and risk model using a case study for Nepal. First, I'd like to introduce the METEOR project. METEOR stands for Modeling Exposure Through Earth Observation Routines. This is a 3-year project funded by the UK Space Agency to look at application of Earth observation technologies to improve our understanding of exposure. Within this project, there is a specific focus on the pilot countries of Nepal and Tanzania. There is a consortium of 8 organizations working on this project. One component of this project is to share knowledge, and this video is a part of a series of videos dedicated to that purpose. This slide shows the main components of risk, which include the hazard, the exposure, and the vulnerability. Risk is the combination of all 3 of these components. This video has a companion video which goes more over the key technical aspects, and if you're interested to learn more on that, I'll refer you to that video. Currently, there are several tools to combine these components and generate useful risk metrics for decision makers in the space of disaster risk reduction. Within this project, and for the particular case of earthquake risk assessment, we are using the OpenQuake engine. This tool is open source, free of charge, and publicly available. Moreover, this tool has been used recently to develop several seismic hazard and risk models for Southeast Asia and Africa, thus allowing anyone to perform their own damage and risk calculations. In order to follow along with these demo exercises, you first need to install and set up OpenQuake Engine. You can download the OpenQuake Engine at the link github.com/gem/oq-engine. Follow along the instructions for your machine type to set up OpenQuake Engine. There is also a manual for further documentation on the OpenQuake Engine. Here you will find all the documentation related to the various features of OpenQuake Engine, input formats, and output formats. There are also additional demos that you can walk through. There are several calculators included within the OpenQuake Engine. On the hazard side, there are 3 calculators. There's Scenario Hazard, Classical Probabilistic Seismic Hazard Assessment, and Event-Based Probabilistic Seismic Hazard Assessment. On the risk side, there's the Scenario Damage or Loss calculators, Classical Damage or Loss calculators, and the Event-Based Damage or Loss calculators. However, within this demonstration, we'll be focusing on the scenario case. So we'll look at the Scenario Hazard, Scenario Damage, and Scenario Risk calculators. Here's a diagram showing the input and output files as they relate to the OpenQuake engine. Since we're focusing on scenario models, those required inputs are shown here. On the input side, we have the ground motion model, the vulnerability model, the VS30 or the site model, and the exposure model. With each of these input files, we can run the desired OpenQuake engine calculator, which might be scenario, scenario damage, or scenario risk. And from that, we can get the following output files. We can get hazard maps, damage maps, and loss maps, as well as statistics on the hazard, damage, and loss. Here are some useful links for OpenQuake. The first is the main OpenQuake site, where you install the OpenQuake engine and also see frequently asked questions. Next is the link to the OpenQuake documentation, so that you can refer to the manual for more details. Then there is the OpenQuake Input Preparation Toolkit, which you can use to build your own model from scratch. Lastly, there is the OpenQuake support forum in case you have any issues in your use of OpenQuake. Once you have OpenQuake installed, there are 2 ways to run the OpenQuake engine. One way is through the command line, and the second way is through the web user interface or web UI. If you're a Windows or PC user, You might see these desktop items set up once you've installed OpenQuake. If you're a Mac user, then you'll be using the command line. In the first demo, I will show an example running a model through both the web user interface and the command line. In the other demos, I will only be using the web user interface. If you are running by the command line, here are some useful basic commands. All of these commands are also documented in the OpenQuake Engine manual. First, to run the model, you'll type in oq space engine space dash dash run, and then the path to your job configuration file. The next line shows how to list all of the outputs from your calculation. After that, we show how to export one result versus all results in the following two lines. Lastly, you can start the web user interface by typing in oq space webui space start. In the first demo, we'll be looking at how to run an earthquake scenario hazard analysis using the OpenQuake engine. Here is a high-level view of the main input and output files for the scenario hazard calculator. The two main inputs you'll need to arrange are the site file and the rupture model. The main output would be the hazard maps. Let's take a deeper look at the different input files for the scenario hazard calculator in OpenQuake. For any OpenQuake calculation, there is always a job configuration file. This file has the extension .ini. This configuration file will also link to other files that are used as inputs, as well as parameters for the analysis. In the case of a scenario hazard calculation, those other files are the rupture model and the site model. Here's an example of the job configuration file for a scenario hazard analysis. Towards the top, we have the description. This is useful for your own purposes when you're looking at previously run calculations to understand which calculation was which. Next, we have the calculation mode. In this case, we're looking at a scenario hazard analysis, and that calculator is simply called scenario. Below that, I have shown an example of what a comment might look like within the job configuration file. These are not used in the analysis, and you can use them however you like, for instance, to document the source of the rupture model or cite some other documentation. Next, we have different parameters that are defining the rupture. We have the rupture model file, so this indicates the path where the rupture model XML is. In the case of a scenario hazard analysis, we are only modeling one particular earthquake rupture event. We also have the rupture mesh spacing. So this indicates the mesh size used to discretize the rupture within OpenQuake, and the units are in kilometers. Smaller numbers for this will mean a refined mesh, but also an increased computational demand. Next, we have the site model file. So this will be the path to which you'll have a CSV that indicate information such as the shear wave velocity or VS30, or potentially other site parameters that are of interest to the ground motion prediction equation in use. Then we have some other inputs for the hazard calculation. One of these is the intensity measured types, which you can put as a list. In this case, we're interested in the peak ground acceleration, or PGA, in the spectral acceleration at 0.3 seconds. Next, we have the ground motion model that is to be used. In this case, we're using Campbell and Bazorgnia 2014. However, you could provide a different ground motion prediction equation name, or even a logic tree of multiple ground motion prediction equations if desired. Next, we have the truncation level. This is used for the ground motion prediction equation, and a truncation level of 3 is fairly standard. This would consider 99.7% of the distribution. and it'll avoid some outliers that are just a symptom of the mathematical model used as opposed to realistic values. Then we have a maximum distance. This is used in case you have some sites that are outside this 500 kilometers in this case. For sites that are 500 kilometers away from the source, the ground motion will not be estimated, and this might be used to save computational space. Next, we have the number of ground motion fields to be produced.
The same earthquake rupture definition could produce different ground motion fields, and this will sample 100 different ground motion fields for that rupture and give a view on the variability of results. Lastly, we have the desired output directory to store our outputs.
Here's an example of the rupture model file. So in the rupture model file, we are defining the scenario, which encompasses the magnitude, the geometry, and the mechanism. In this case, we're looking at a single plane rupture with a magnitude 7.8 events, a rake of 100 degrees, and a hypocenter as indicated here. And we are defining the rupture surface with these 4 different coordinates.
In this particular example, we are using the parameters described by the U.S. Geological Survey's finite fault model for the 2015 Gorka earthquake event. In order to build your own rupture model file from scratch, we recommend you use the Input Preparation Toolkit, which is linked at the bottom.
Here there's a web user interface where you can specify the different inputs, such as the locations of the rupture boundaries and the hypocenter location.
And it will automatically generate this rupture model XML file for you. Here's an example of the site model file. This is a CSV that contains the geolocation, or long lat, of the various sites in the model. In addition, we include some additional site terms that are used by the ground motion prediction equation. In this particular example, we are using values interpolated from the USGS Global VS30 map, which is available at the link there.
Also within the configuration file, we identified which ground motion model or ground motion models we would like to use. The OpenQuake engine has a library of over 100 ground motion prediction equations, and you can go to the link here in order to see a full list of those. Now that we've covered all of the inputs to the scenario hazard analysis, let's go and run the model. We will run this model in 2 different ways. We will run the model first using the web user interface, and then we will follow up and run the model using the console instead. We'll start by opening the OpenQuake web user interface. If you're a PC user, you should have a desktop icon that you can double-click. Whether you're a Mac user or a PC user, you can also start up the web user interface by the command line. For PC users, the command line is the OpenQuake console that is installed when you install OpenQuake. For Mac users, the console is the terminal app. In either case, at the command line to start the web user interface, type in OQ space web UI space start. Once you hit enter, your default browser should open up a window with the OpenQuake web UI. Do not close the command line while using the web user interface. In the web user interface, you will see a list of any calculations that were previously run and the option to run a new calculation. To run a new calculation, simply zip all of your input files and load it in. Let's start with the example for scenario hazard. To run demo number 1, the scenario hazard demo, First, locate where you download demos files. Within that, find the hazard subfolder. Within the hazard subfolder, you should have 3 different input files. Compress those 3 files into one zip file. Feel free to rename that file to anything of your choosing. Next, go back to the OpenQuake web user interface and click on Run a Calculation. Locate the zip file you just created and double-click to load that. Once you've done that, you should see a new calculation appear with the description as you wrote it in the job configuration file. There will also be the calculation ID and the calculation mode indicated here. While the calculation is running, you will see the row is yellow. Once the run has completed, it will turn either green or red depending on whether the calculation was successful or not. This process could take seconds to minutes. Once the run has completed, you will see a few action buttons appear. You can click on the console to see a log of your analysis. At the end of the log, you will also see the amount of time the calculation took. In this case, the calculation took 43 seconds. The log is also useful as it reports errors or warnings in case the calculation was not successful. Next, click on Outputs, and you'll see a list of different outputs you can download from the calculation. Some key outputs from a scenario hazard calculation might be the events file or the ground motion fields file. You can click the download action to download that file. In addition, you'll see an output that is the full report for this calculation, as well as an output that is a zip file of all the inputs used in the calculation. Each of the output IDs is also shown on the left. Additionally, you can download all of the data written during the calculation by downloading the HDF5 data store. This might be useful if there is some custom post-processing that you would like to do. Back to the presentation, I'll explain some of the key outputs from the scenario hazard model. Now let's cover some of the outputs from the scenario hazard calculation. 2 of the main outputs I'm highlighting here. One is called the site mesh, and the other is called GMF, or ground motion field data. For the site mesh, we'll have each of the different site IDs as defined by the OpenQuake engine and their respective geolocation, or their long lats. Within the ground motion field data file, we'll have the site IDs, which are the same as the site IDs shown here, the event IDs, and then the ground motion values, or GMVs, for each of the desired intensity measures. In this case, we are looking at 4 different intensity measures: the peak ground acceleration, or PGA, the spectral acceleration at 0.3 seconds, spectral acceleration at 0.6 seconds, and the spectral acceleration at 1 second. In this file, the number of rows will be equal to the number of sites multiplied by the number of ground motion fields requested in the job configuration file. In the demo file provided, there were 100 ground motion fields requested, which means that there will be 100 different unique event IDs within this file. Here's an example of the ground motion field data being overlaid onto a map. So in this case, we're looking at the estimated spectral acceleration at 0.3 seconds. Scenario hazard analyses might also be useful to verify a larger model with historic events. In this example, we were looking at the 2015 Gorka events And we're comparing the estimated peak ground accelerations recorded from different stations within the Kathmandu Valley. For our second demo, we will be performing an earthquake scenario damage analysis using the OpenQuake engine. Here's an overview of the various input and output files used by the OpenQuake engine. Here we have the same two input files that were indicated earlier for a scenario hazard analysis, that is, the site file and the rupture model, which we went over in demo number 1. In addition to that, we'll have the exposure model, the fragility model, and the configuration file, which will link to all of these other files.
Outputs from the scenario damage calculation include damage distributions and maps.
Here's a closer look at the various input files required by the scenario damage calculator within OpenQuake. As before, we have the job configuration file, which then points to a few additional files that are used as inputs. Similar to the scenario hazard calculation, we have the rupture model and the site model. However, in this case, we also have some additional inputs, which I'm referring to as the exposure model and the vulnerability model. In this case, we have an exposure XML file, which is linking to an exposure CSV file. It is also possible to link to multiple exposure CSV files, such as if we were to differentiate between different occupancies within the region. Within the vulnerability model, we have a CSV file that defines a mapping between the exposure taxonomy and the vulnerability taxonomy. In this case, we are using a set of fragility curves. So this is looking at structural fragility in our XML file. Here's an example of the scenario damage job configuration file. As before, we have a description, which will be helpful to us when we're looking at our outputs and want to identify which runner is which. In this case, we're changing our calculation mode from scenario to scenario_damage. We have many of the same inputs as before in the hazard calculation, which references the rupture model and the site model, but I have truncated those here so that we can highlight the new inputs. The new inputs include the exposure file, the path indicated here as exposure.xml, and the taxonomy mapping file with the path indicated here, and the structural fragility file with the path as indicated here. Next, we have also added a minimum intensity parameter. In this case, for each of the different intensity measures cited, we're looking at a minimum intensity of 0.05 G to incur damage. This can help us save space and time in the calculation, since it is unrealistic that we will have damage at levels of shaking that are that low. And so we do not need to take the extra step into calculating damage if the ground motion field value at a given point is less than this specified minimum intensity. And lastly, we again have a reference to the desired output directory at the bottom. Here is an example of the scenario damage exposure model file. So in this case, we have a description of the model, as indicated here. And then we have, for each of our loss types that we want to consider, the type of cost and the type of units. You can also add some additional tags in case they are of interest. This may be useful to you if you want to aggregate your results by some field, such as by a county or jurisdiction. Lastly, we reference the exposure CSV file or files under the assets tag. Here's an example of that exposure CSV file. In this file, you can have many attributes if you choose, but some attributes are required. The required attributes include a unique ID, the geolocation or long lat, the taxonomy building class, the number of buildings at that site and within that class, and the replacement value, or the value for each loss type that you want to consider. In this case, we are only looking at a structural loss type, and so that is indicated there. But additionally, you can include any additional attributes that will be helpful for you.
Here's a visualization of the provided exposure data. In this case, we're looking at the structural residential value aggregated at administrative level 4.
Then there is the taxonomy map file. So this allows us to consider a different exposure building class to vulnerability building class. In this particular case, we have a direct one-to-one mapping where our exposure class is the same as the vulnerability class. However, OpenQuake allows us to have a difference here, and you could supply an alternate conversion in this column. Additionally, if you want to consider uncertainty in the mapping from the exposure class to the vulnerability class, you could choose multiple different conversion options and supply their relative weights here. Another input is the fragility model file, and here's an example XML. Within the fragility model XML, we define each of the limit states that are being considered. So in this case, we're considering slight, moderate, extensive, and complete. Then for each unique building class, in this case, we are looking at this first ID here, we can provide the IMLs, or the intensity measure levels, and the probability of exceedance, the POEs, for each of the limit states. This IMLs tag defines the x-axis and the x-axis units. The POEs tag supplies the y-axis values. Together, this defines the fragility functions for each building class. Now that we have discussed all of the inputs, let's run the model. Now we will run demo 2, the scenario damage model. The process is the same. First, locate the demos folder, and then identify where the damage subfolder is. Select all of the input files and then compress into a zip file. Feel free to rename to any name of your choosing. Next, go to the web user interface and click on Run a Calculation. Once you've found the zip file you just created, double-click it. Once again, you will see a new row appear in yellow while the calculation is being completed. This could take seconds or minutes to complete. Once the run is completed, you should see that it is green or red, and it will be green if it is successful. Similarly, you can click on the Outputs button and see the different outputs that are available for download. Now that we've completed our analysis, let's look at some of the main outputs. Two of the main outputs I'm highlighting here. One of these is called damage by events, and the other is called damages. In the damage by event CSV, we get aggregated counts of assets in each damage state. Then for the damages CSV, we get the count in each damage state on a site-by-site basis. In this file, we also have retained any tags that we specified in the exposure XML file. In this case, we wanted to also have the ID_4 field. This damages CSV will be produced for each realization. In this demo, we only had one realization because we were only considering one ground motion model. However, you could also provide a logic tree that would indicate multiple ground motion prediction equations and therefore have more realizations. Visualizing this data, we can see the estimated number of buildings in slight, moderate, extensive, or complete damage states. Here is a map showing the proportion of buildings in the slight damage state, in the moderate damage state, in the extensive damage state, and finally in the complete damage state. In the third demo, we'll be looking at an earthquake scenario risk calculation using the OpenQuake engine. Here is an overview of the main input and output files associated with a scenario risk calculation. As with the previous demos, we have the site file and the rupture model, which are inputs to the hazard calculations, which are a part of this analysis. Then we have a job configuration file, which will also link to these other input files, our exposure model, and our vulnerability model. In comparison to demo number 2, which looked at a scenario damage calculation, the main difference here is that we are using vulnerability curves rather than fragility curves, which means that rather than providing a probability of exceedance of a given damage state, we're going to be providing an expected loss. This allows us to then calculate loss maps and loss statistics, which are outputs of the scenario risk calculation. Here's a closer look at the input files involved. As with any OpenQuake analysis, we have the job configuration file, which links to many of the other inputs. So here we are again linking to the files required by the hazard portion of the calculation, so the rupture model and the site model. And we are linking again to our same exposure model as we used in demo number 2. As for the vulnerability model, we once again have a taxonomy map CSV, but we have swapped from the structural fragility XML to a structural vulnerability XML here. Here's a look at the example job configuration file for a scenario risk calculation. Once again, we have the description of the analysis. Then we have our calculation mode, which in this case is scenario_risk. Similar to demo number 2, we have our exposure file, and we have our taxonomy mapping CSV. However, in this case, because we're interested in losses, we've swapped from a structural fragility file to a structural vulnerability file. And in this case, the path to that file is structural_vulnerability.xml. Then, similar to demo number 2, we have minimum intensities specified so that we can save some space and time in our calculation and avoid calculating losses at intensity levels that are so low we do not expect there to be damage. And lastly, we again have a location of our desired output directory. Here's a screenshot of the vulnerability model file. In this case, we have a vulnerability curve defined for each building class. In this screen capture, we can see 2 building classes with vulnerability models defined, their ID being here and here. Then, within each of these vulnerability function definitions, there are 3 additional parameters that are specified. The IMLs tag defines the x-axis values, as well as the units of the x-axis. The mean LRs tag defines the mean value of loss ratio given each of these x values, and that defines the values on the y-axis. Lastly, the COVLRs tag defines a coefficient of variation of the loss ratio at each intensity level. So this defines a distribution around the y-axis values, which are provided in mean LRS. In this particular example, we are considering 0 or no distribution for each of those mean loss ratio values. Now that we've taken a look at our new inputs, let's go ahead and run the scenario risk model.
Now we're going to run demo number 3, the scenario risk model. First, identify the location where you saved all the demos files, and within that, find the risk subfolder. Select all of the files and compress into a zip file. Feel free to rename the zip file to any name of your choosing. Once that is done, go back to the OpenQuake web user interface and click on Run a Calculation. Locate the zip file that you just created. Once you found the zip file, double-click. Now you should see a new yellow row appear, and it will stay yellow while the calculation is completing. This process could take seconds to minutes. Once the run is completed, it will turn green if successful. Similar to the previous exercises, you can click the Outputs action to download the various results. Going back to the slides, we'll discuss some of these key results.
Now that we've completed our scenario risk model, let's take a look at some of the key outputs from this calculation. 3 of the key outputs are ag losses, or aggregated losses. This gives you the statistics for the aggregated loss, so across all sites. So in this case, we get our mean and our standard deviation. Then there's the average losses mean CSV. So this provides the mean losses for each site across all the realizations. In this particular example, we only considered one ground motion model, which means that we only had one realization. However, if we considered a ground motion model logic tree, we might have multiple realizations, and this would provide us the average losses across those realizations. Next, we have average losses -RLZ, or realization, which will provide the realized losses for each site. So this file will exist for each realization that we have run. Again, in this case, we are only considering one ground motion model, which means we only have one realization, which means that the values in this CSV will exactly match the values in this mean CSV. If we visualize these outputs, this is what we get for the scenario losses. However, it might also be useful to normalize those scenario losses by the total exposed value in that area so that you can get a loss ratio.
This concludes the 3 demo exercises for earthquake scenario hazard and risk modeling. Thank you for watching.